When you look at event increments, you will see that its guard specifies the scenario where the value of f at index r is less than the target value v. And to visualize it, look at this diagram here. F of r is less than the target value v. And in this case, we decide to increment the value of p by assigning that to the value of r plus 1. And just look at another diagram here. So now the p value after the execution of the events becomes r plus 1. And another action we will do in parallel would be r is assigned non-deterministically from a new range, which is from r plus 1 up to q. So you can see from r plus 1 up to q. So from there, we'll actually get a new value of r, and from there, we'll keep going with our search process. So let's just go back to the Rodin platform. These two actions of assigning r plus 1 to p and assigning r plus 1 as a lower bound for the new value of r. So these two actions actually generates two proof obligations with respect to invariance number 1, because we are actually now increasing the value of p, and we want to make sure the new value of p, which is now r plus 1, is still in the range of 1 up to n. And the second one would be that the new value of r can really be assigned by assuring that r plus 1 up to q is actually non-empty. So these two conditions correspond to, first of all, this guy over here, so which is to prove that r plus 1, which is the new value of p, is still in the range of 1 up to n according to invariant 1. And the second one, the second proof obligation to discharge would be related to the feasibility of action 2. Let's have a look. And here you can see that the thing we want to prove is the range of r plus 1 up to q is non-empty, which means when we want to do the non-deterministic assignment to r, we want to make sure there's really some non-empty set of values for us to choose from. Okay, so these two proof obligations have things to do with the new value of r, which is r plus 1. So now, let's go back to the diagram. And let's just summarize. So these are this is the guard for the event increments, and these are the two actions which will generate the two proof obligations that we are trying to discharge. And to prove we want to take care of these two proof obligations, the first one is to make sure the new value of p is still in the range of 1 up to n. And the second one to prove is to make sure that the new range from r plus 1 up to q is non-empty. And to prove these two, we claim that it is sufficient to add an extra guard or an extra theorem to the event's increments, and we will simply just do r less than q. If you see from the diagram, the thing we want to prove is that because r is actually less than q, so when we actually increment the value of p, we actually get up to here, and we still have some value to search from in between. So that's the intuition for the new theorem. So what you have to do, let's go back to the Rodin, is to add an extra guard to the event's increments. Let's just go there and let's add an extra guard here. So right click, add guard, and here we'd say, we have to say r is less than q. And what we want to do is not to declare that as not a theorem. Instead, we want to say it's a theorem because we want to prove that this can be inferred from the guard, existing guard over here. If you actually declare this as not a theorem, then you will actually still have to prove it. You will actually be propagated to the next level of refinement, which is not our intention. We want to prove that R is less than Q and want to prove it now at this level. Okay, if you save it, you will see that the two proof obligations that we talk about are now actually discharged. However, we have to prove that the guard number 2 is really a theorem before we can conclude the current phase. Okay, so in the next video, we'll talk about how to prove that R is less than Q as a derived theorem for event increments.